Hello friends, I am Dr. Bhavik Suthar, Associate Professor in Electrical Engineering Department at LD College of Engineering. Today we will be discussing about the power factor, complex power, that is active and reactive power, apparent power, and its RMS values and instantaneous values in resistive, inductive, capacitive, and both R, L and C circuits. So the lecture is arranged in this way. First of all, we will be discussing about the waveforms of voltage and current, sinusoidal waveforms of voltage and currents, then how it behaves in various component of the circuit like resistive circuit or capacitive circuit or inductive circuit, and then how to find out the power in those circuits from the waveforms, and various types of powers we'll discuss about the active power, reactive power, and from that what is the complex power, and then we'll derive the equations for RMS value of the active power, reactive power, similarly instantaneous values of active power, reactive power, and then we'll finally discuss about the power factor in a circuit. So let us go to the telenote and discuss about the RLC circuit. So let us discuss the circuit like this, where we have the voltage source Vs and a resistive element like this, where we have R. When we apply the Vs, there are different types of sources, like we have DC source or AC source. In AC source also different types of waveforms. We will be discussing about the sinusoidal waveform first. So let us say that we are applying the sinusoidal waveform Vs is equal to Vm sine omega t plus theta. This is the waveform which we apply to the circuit. Mind well, the circuit is a resistive circuit, and because of this voltage supply, the current I will flow through this circuit. Now, in the previous lectures, the madam has already discussed about the instantaneous values and RMS values and average values in AC circuit or DC circuit. So this form of the voltage waveform is basically the instantaneous, because it contains T. So with respect to time, how the voltage is varying, so at every instant of the time we can get the value of the voltage. So this is known as the instantaneous value presentation. Similarly, when we apply this type of voltage to the circuit, we'll have current flowing through the circuit, and it can also be represented by Im sine omega t plus theta. Because it is the resistive circuit, there will not be any phase difference between the voltage waveform and current waveform. So when we draw the waveform of the voltage and current for the circuit, it will be in phase like this. So this will be the Vm, this will be the Im, and this x-axis is a time axis, and this is the magnitude for voltage as well as current. Now instead of resistive circuit, suppose we have the inductive circuit like this. And same way, when we have the inductive circuit, same voltage is applied to this inductive circuit. V of t is equal to Vm sine omega t plus theta, and if we find out the expression of it, we can say that it will be displaced by 90 degree. That is already discussed. So if we draw the waveform for the inductive circuit, here after 90 degree the current waveform will start. Now we can see here the phase difference is exactly 90 degree because it is a pure inductive circuit. Similarly, in a capacitive circuit, Vm sine omega t plus theta, when we draw the I, it will be 90 degree leading. So when we draw the voltage waveforms and current waveform, it will be 90 degree leading. So from these three, we can find out the instantaneous power flowing through the resistive circuit, through the inductive circuit or capacitive circuit. So as you all know, the expression of power P is nothing but it is V into I. Now this V into I, when we write V into I, normally this value of V and value of I is a RMS value, and from these two values we can find out the RMS value of the power. But if we want to find out the instantaneous values of the power, then for instantaneous values of the power we have to multiply the instantaneous value of the voltage and instantaneous value of the current. Now we have already drawn the instantaneous values of voltage and current in this waveform. So here, if I want to find out the power in a purely resistive circuit, I can draw the waveform of power like this. Now here we can go to the slide and we can have the exact diagram of the waveform, power waveform for resistive load. From the diagram we can see that as the value of current and voltage both are positive, the value of power is positive. Here the black waveform shows the voltage waveform, red waveform is the current waveform, and the third one, that is blue one, is the power waveform. Here we can see that for first 180 degrees both the value of the voltage and currents are positive, and that is why the power is also positive. While for next 180 degrees, the values of the voltage and currents are negative, but because we multiply both the values, negative negative becomes positive, and we can see that the power also positive. So from the graph we can say that the value of the power never becomes negative. It always remains positive. Now when we talk about the circuit, in the circuit, when we supply the electric power to the circuit, the energy from the one form to the another form can be transferred, and when the energy transferred, there are four possible things which can happen. The first thing is the energy can be transferred to the required form of the energy. So here the energy is in the electrical form and it can be converted into another form of energy. It can be converted into mechanical energy or chemical or another type of energy. While doing so, there may be three more things which may happen. The another thing is, it may happen, we may have the energy loss in the circuit during the transition. Second thing which happens is, we can store the energy. So when we talk about storing the energy, it can be stored in two forms. One, it is in the kinetic form, and another one is in the potential form. In the kinetic form, the energy can be stored in inductor, that is 1/2 L square I, and another is in the potential form, that is in the capacitive elements. So these four things happens. Out of these four things, we are interested in converting the energy, so this energy will be useful. Other types of energy, it may be loss or it may be mere a transfer of energy from one form to another and another form to one form, but it cannot be converted and it is not the useful. So when we talk about the resistive circuit, when we go to the graph and see the resistive circuit, we can see that the power is always positive, and we can say that because the power is positive, the energy is flowing from source to the load. So here in the resistive load, the power will be transferred to the resistance. Okay. Now, if we draw the instantaneous value of the power, in the instantaneous value of the power in the inductive load, again we can see that the voltage waveform, black voltage waveform, is starting from 0, it is increasing, so it is a simple sine wave. Then we have the red waveform, that is the current waveform, and in the inductive load, the current is lagging behind by 90 degrees. See, in electrical engineering, we can say that when the vector is rotated, it is always 90 degree ahead when it is leading, and it is 90 degree behind when it is lagging. So in inductive load, it is lagging by 90 degree in pure inductive load. So from this voltage waveform and current waveform, if we want to find out the power, instantaneous values of the power, again similarly we will have to multiply the instantaneous value of the voltage waveform and instantaneous value of the current waveform. So the blue line in the graph will be the multiplication of instantaneous value of voltage and instantaneous value of current. We can see from the graph that the power here is negative for initial 90 degrees and then positive for next 90 degrees. So in one half cycle, we can say one cycle is completed. So we can say that the frequency of power is double the frequency of voltage waveform or current waveform, and the magnitude of power becomes negative, positive, negative, positive, and so on. Now, the meaning of positive power we have already discussed in the resistive load, but when we talk about the inductive load, we can see that power also becomes negative. Instantaneous power also becomes negative. The meaning of negative power means the energy is extracted back from the load to the source, and positive power means the energy is transferred from source to the load. And if we find out the average value of this power waveform, it becomes 0. That means the useful power which will be used by the circuit or which will be converted into the required form is 0. So in this circuit, we can say that power is oscillating, means the power energy is transferred from source to load and load to source, source to load and loads to source. But the useful power available, that is the useful power or average power, it is 0. So we can conclude that in the inductive load, the useful power or average power is 0, but the power is oscillating with double the frequency of the supply voltage frequency or current frequency. It is oscillating. So now, after discussing the inductive load, let us go to the capacitive load. For capacitive load, as we have discussed, the voltage of waveform is black, voltage of current waveform is red, and the instantaneous power waveform or waveform of the voltage of the power is blue. Again, similar to the inductive circuit, in capacitive circuit also the blue waveform is similar. Only difference is earlier it was negative first and then it becomes positive. Here it is positive first and then it becomes negative. Otherwise, if we talk about the average power which is being transferred from the source to the load, that average power is again 0, similar to the inductive load. So here also the same case, whether it is a inductive load or a capacitive load, pure inductive load or pure capacitive load, the power will never be transferred from the source to load, but it is oscillating with double frequency. Now, from this we can come to the another definition, that is the power factor. Power factor. Now the power factor is nothing but when you have the resistive power, when you have the resistive load, your waveform will always be positive and you will have some average power, and this is the average power which will be transferred to from the source to the load. Now if you have we can say if you have the inductive or capacitive load, this waveform would be like this, and the average value of this power is 0. Now if we have the combination of both, then combination of both means suppose we have R element, L element, or we have R element and C element, or we may have R, L and C element, whichever may be there, but the effective R L circuit or R and C circuit will have the waveform of power would be like this. That means it will be the combination of these two waveforms depending upon the quantity of R and quantity of L. If you have L0 and 100% R, your waveform would be like this. If you have R0 and 100% L, your waveform would be like this. And depending upon the contribution of R and L in the circuit, you may have the power waveform like this. Now from this power waveform, we can see that this is the positive element and this portion is negative. Now this positive, let us say it is A, and negative, let us say it is B. We can say that positive means this is the power which is being used by the circuit, and this is the power which is not being used but it is transferring because it is negative, so it is extracted back by the source. Now when we talk about the power factor is nothing but it is the measure of the degree to which any given load means it may be combination of any combination of R, L and C, which any given load matches to a pure resistive load. So for pure resistive load, you have P is equal to V into I, but for P load, which is not a pure resistive load, you have something else. So P load divided by PR will give you the power factor. So this definition of power factor is useful for any type of waveform. See, normally in electrical engineering, we deal with sinusoidal waveform. But in actual practice, it may happen your waveform may not be sinusoidal. So let us say your waveform is like this. Or it may be like this. So for any kind of waveform, if you are in a position to find out what is the PR and what is the P load, then from the ratio of PR and P load, you will be able to find out the power factor of a circuit. Okay. Now let us discuss about the real power, reactive power and complex power of the circuit. Complex power of the circuit. Now, as you all know, in RL circuit, if you represent the voltage and current waveform in phasor form, it will be V and I, like this. Now mind well, these values are not the instantaneous values. These values are RMS values, and the angle between these two vectors is, let us say, theta. Now if we want to find out the real part and the imaginary part of multiplication of these two vectors, then we have real part along the x-axis and imaginary part may be across the y-axis. It may be on the above the x-axis or it may be below the x-axis. Now if we take the component of I on the V, we can see that the P will come, that is the active power will come in this direction, and the reactive power, that is the imaginary part, will come in this way. So here we will have the reactive power. Normally it is denoted by Q. Now this Q, you can see it is on the negative y-axis. So I want to represent this P plus Q in the complex plane. It will be P minus JQ. It will be P minus JQ. But when you have the inductive load, normally this is taken as positive. So it should be P plus JQ. For inductive load, it should be P plus JQ. If we take the current vector here as actual lagging current, then this Q comes negative. And that is why when we find out the complex power S, normally we multiply V with I conjugate. So when we take the conjugate of the current, it is reflected on the opposite side. So now my I conjugate would be in the upper side and the angle will be same. So my reactive power would be over here. And now this formula of complex power for inductive load, that is S should be equal to P plus JQ, will become true. And that is why we normally in the way, while we finding out the complex power, we normally take the conjugate of the current vector. Okay. Now let us try to find out the instantaneous values of real power, reactive power and complex power. So again, let us take voltage waveform. Vt is equal to Vm. Let us take cos now, cos omega t plus theta v. And I is equal to IT, that is equal to Im cos omega t plus theta I. Mind well, this theta v is the angle of voltage waveform and theta I is the current angle of current vector. Now, when we want to find out the instantaneous values, the expression is V of t multiplied by I of t. So this is equal to the multiplication of Vm cos omega t plus theta v into Im cos omega t plus theta I. So we can simplify these as Vm Im cos omega t plus theta v into cos omega t plus theta I. So using the trigonometrical identity, we can find out, or we can simplify this as 1/2 Vm Im into bracket cos theta v minus theta I plus cos 2 omega t plus theta v plus theta I. Slightly rearranging, we can write 1/2 Vm Im cos theta v minus theta I plus cos 2 omega t plus theta v minus theta v minus theta I. This is just rearranging it, and now from this, using the trigonometrical identity, we can directly write 1/2 Vm Im cos theta into bracket 1 plus cos 2 omega t plus theta v plus 1/2 Vm Im sin theta into sin 2 omega t plus theta v. Now this is the part 1 of the power, instantaneous power, and this is part 2 of the power. Now part 1 of the power, we can say that it is nothing but it is the Vi cos phi or cos theta, where theta is the angle between the voltage magnitude and current magnitude and current phasor, it is the angle between the voltage phasor and current factor. and this V and I are basically the RMS values of the voltage waveform and current waveform. This second portion of part 1 is basically a oscillating component. It is pulsating at twice the frequency, and the second property of this component is it never becomes negative. That means it is the unidirectional power flow, and so it flows from source to load, and that is why this is known as the active power. This is normally referred as active power. Now this second component, if we draw the waveform of the second component, it is basically oscillating, and this component has double the frequency with zero average value. Now, the careful study of this part, we can see that if the circuit is inductive, this theta will become 90 degree, and so the average power will become 0. The load is purely capacitive, then current leads by the voltage by 90 degree, and again the average power is 0. So this expression will tell you all about the instantaneous power in the system. So from this again we can draw the another triangle. That triangle is known as the power triangle. So in the power triangle we have the real power on the x-axis. This may be P. This is the reactive power Q, and this will be the S. Now, if you want to measure the power factor in RLC circuit, again you can have the another triangle, that is V is equal to IR. This is VL, that is equal to I into XL, and this is equal to VZ, or that is equal to I into Z. Now from this and trigonometrical ratio you can find out the angle also, and this angle is known as power factor angle. Now, if you want to measure the power factor or power factor angle using voltmeter, it is possible. What you can do is, you can find out the voltage across all the elements. You can find out the voltage across VR, and the ratio of VR upon VZ, you can find out the angle, and from that you can find out the power factor also, or vice versa. From the power factor you can find out the angle also. So here in conclusion we can see that the series RLC circuit, the active power, reactive power, complex power and power factor are very important thing as far as the energy consumed, energy dissipated, and energy used is concerned in the electrical circuit. We have seen that when the power factor is unity, when PR and P load are equal, the total energy which is supplied will be used or will be converted into useful form. If the power factor is not unity, then in that case, some of the energy, depending upon the value of the power factor, some of the energy will be stored in the elements like inductor or capacitor, and this energy will again be extracted back by the source. Now, we have also discussed about the instantaneous value and RMS values of active power, reactive power, and complex power. We have seen that the instantaneous value of real power is pulsating. We have seen that the instantaneous value of reactive power for purely inductive and capacitive load is changing from positive to negative and negative to positive. I am talking about instantaneous. And the average value is 0. Its average value is 0. Now, when you have the poor power factor in the circuit in the actual system, what happens? For getting the same amount of energy converted into useful forms, your value of the current will be more. And when you have more current to supply, or when you have more current in the line or in the system, you require thicker conductor, then you require more current to flow, and whenever we want that more current is flowing in the circuit, then its heating losses will be more, and there will be a less amount of useful power. And that is why the poor power factor or the less power factor is discouraged in electrical power systems, and that is why the utility companies are penalizing the consumers who are using the load with poor power factor. So as a remedial case, what happens? We can connect the capacitors in parallel with the inductive load or vice versa, and then we can improve the power factor in the system. Now, when we connect the capacitor in the circuit, what happens? The energy which was earlier oscillating between the source and load, now it will oscillate between the potential energy to kinetic energy and kinetic energy to potential energy. That means the energy will oscillate between the inductive element and capacitive element, or between the capacitive element and inductive element, and that is why this energy will not flow from source to the load. And this is how the flow of energy from the source to the load can be removed. That is why we connect capacitor to improve the power factor, and power factor is kept unity in a power system. Thank you very much.